Hello, everyone, and welcome to our presentation entitled Lean Approach to Application Modernization. My name is Lucas Ho. I'm a product manager at Tanzu Labs, situated in the Singapore office.
Hey everyone, this is Mushtaq Ahmed. I'm a solutions architect based out in Tanzu Labs, Bangalore.
Today, we will be discussing how we utilize lean concepts to application modernization. We'll first talk about what we mean by lean and its benefits. Then we'll talk about how Tanzu Labs utilizes the Swift methodology in application modernization engagements. And finally, we'll look under the hood to discuss the patterns we use to decompose the monolithic architectures we face with enterprises. At present, enterprises are faced with a need to migrate their legacy systems into cloud-native architectures via microservices. At a glance, legacy architecture presents problems for enterprises. First, the complexity is directly correlated to time, as monolithic systems are built over a span of several years. Second, it elongates the software development lifecycle when trying to enhance the system with new features due to its tightly coupled nature. Third, it degrades developers' experience due to the significant overhead costs from heavy processes. And lastly, as time and the complexity of the architecture increase, so too are the operational expenditures required to maintain expensive licenses and maintenance. The challenge is to migrate to a microservice-based architecture without major disruption and outage to existing client systems. Traditional development utilizes a waterfall approach. From requirements gathering, planning, development, and testing, the time elapsed through this lengthy approach represents a significant increase in risk. The only true way to pay down this risk is to ship something, see how users respond, see if that response drives your business outcomes, and adjust. The best way to manage this risk is to make the batches of work that flow through the process smaller, so cycle time through the whole system is shorter and you get more feedback loops. The risk of being wrong is lower and your time to learning is shorter. By approaching software using a lean approach, we can ensure that we properly manage the amount of risk by using that said feedback loop. Popularized in the book titled Lean Startup by Eric Ries, the build, measure, learn loop has become synonymous with application and business development. First, it allows the team to build manageable sizes of the service. Then we push the service to a live environment in order to measure feedback. And finally, it allows us to learn from our findings so we can decide whether to pivot or persevere. When we partner with enterprises to modernize their applications, we ground ourselves in principles throughout the engagement process. The first principle involves us starting from scratch by focusing on developing new microservices using a new tech stack. The second principle gives us the best chance to achieve positive outcomes through small increments instead of trying to modernize in one go. Third, we want to ensure that we iterate quickly in building our notional architecture so we can achieve the established business outcomes. And last but not least, our ability to learn as a team through these tight feedback loops allows us to scale at a breakneck speed. The set of lightweight techniques you see here embodies the Swift methodology we use for application modernization. Created by Sean Anderson at Tanzu Labs, it utilizes agile and domain-driven design principles to help teams plan just enough to get started. This represents an opportunity for the teams to go through a cycle within weeks, not months or years. Let's start with event storming. By including subject matter experts from the appropriate business segments and gathering them in the same room with one another, we're able to focus on the business layer without needing to speak at a technical level. By discussing business flows within the respective domain, we are able to discover insights, risks, and opportunities for modernization. From event storming, we will have many flows describing a business domain. Instead of trying to solve the entire business events in one go, we want to take a thin slice or a group of events covering a succinct business narrative in order to start our modernization efforts. This lean approach allows us to realize incremental value while minimizing risk. After carving out that thin slice to start with, we then model relationships between the business capabilities from our event storming exercise. This allows us to generate our notional architecture. From a lean perspective, our notional architecture is essentially an assumption on paper. This starting point allows us to test the interaction and further refine our aggregate candidates. We spent the first part of our presentation discussing at a high level the concepts, principles, and methodologies we use to decompose a large monolithic system into its respective microservices. My friend Mushtaq will now discuss how we go about decomposing the monolith and what patterns we use to support incremental modernization.
Thanks, Lucas. Right, so just to start off with, we're looking at some of the patterns around decomposing a big, large legacy monolith into microservices. There are many patterns, but we have tried and tested the following patterns: the Strangler fig pattern, anti-corruption, branch abstraction, and change data capture. Now we'll go through each one of these and we'll see what are the pros and cons of each of these approach and how we have gone about using these in actual engagements. So let's start with the Strangler fig tree. So this is one of the most common technique in application modernization. It was first coined by Martin Fowler. It was inspired by a certain type of fig that seeds itself in the top branches of trees. The fig then descends towards the ground to take root, gradually enveloping the original tree. At first, the existing tree becomes a support structure for the new fig, but eventually the fig grows into a beautiful structure, fully self-supporting, where it starts consuming the nutrients and resources from the original tree, leaving it to die and rot. So in the context of app modernization, we can draw a parallel here, where we can incrementally build microservices that replicate functionality of the existing monolith. The idea is that the old legacy monolith and the new microservice can coexist in a production-like environment, and we can evolve our new services over time with the same functionality provided by monolith. And eventually, we end up replacing the old legacy system with a set of new microservices. So how does this work? Implementing a Strangler fig pattern relies on 3 steps and it goes in a cycle group. So as a first step, we need to quickly identify a part of the existing system that needs to be migrated. So in this example, we have 2 functionalities, A and B, and we would ideally want to migrate the functionality A into its own independent microservice. Step 2 would be to basically implement the new functionality as a new microservice. Step 3 would be to then bring in a new component called as a proxy component, which can reroute calls from the monolith to the new microservice. It is worth noting that as in step 2, you can have the new service deployed into a production environment and wait until the functionality is fully tested, with the understanding that no live traffic is handled by the new service. So this helps us mitigate risk and ensure that at any point of time, we have full comfort and knowledge that our new service can be fully tested and deployed. One of the key features of this pattern is that not only you can incrementally migrate the monolith application, but you can also roll back if you notice any problems with the new functionality. Right? One of the biggest benefits of this pattern is also that you have 0 to minimal changes done to the monolith. The key challenge for this pattern is that when you have the functionalities within the monolith very deep inside the system and are very tightly integrated then it makes it difficult to forward requests from outside to the component. So, we discussed about the proxy being a layer to rerouting traffic. So there are different ways we can implement the proxy. and it all depends upon how the monolith receives incoming traffic. So if the monolith uses HTTP, you could use a dedicated proxy such as Nginx that supports redirection based on URI path or method types. If, for example, the monolith is driven by receiving messages via a message broker, we can change the monolith and have it ignore messages which will be consumed by a new microservice. Here we have both a new service and the monolith share the same queue, and they use filtering to listen to messages they are interested in. This example we implemented in one of the engagements was we used JMS message selectors in the monolith to ignore messages, and those messages were eventually consumed by a new microservice. A third scenario is where the monolith receives inbound traffic using a legacy protocol. For example, the monolith currently exposes a SOAP-based HTTP interface, but the new microservice is going to support a REST-based interface. We could then configure a proxy that transforms the request and responses accordingly. There are many ways we can implement the proxy to intercept the calls, the existing monolith, and redirect to the new service. For example, you might have a monolith which consumes a file using an FTP-based interface, or can receive a bulk file upload through a HTTP-based interface. You could all handle this in a proxy-based interception, thus allowing the new microservice to handle those requests. So as we saw in the previous slide, the Strangler pattern allows us to have the old and the new implementation coexist at the same time. Once we have the new service implementation ready and accept live traffic, we can use the parallel run pattern to give us the confidence that the new functionality is working as intended. Rather than redirecting traffic to either the old or the new implementation, we call both, which allows us to compare the results to ensure that they are equivalent. We can use this technique not to just verify the functionality of the new implementation, but at the same time, we can also look at some of the non-functional requirements such as the response time or the latency issues, any of those issues. In either cases, the old implementation is always considered the source of truth, well, where there are any differences observed during the parallel run. So obviously one of the biggest challenges as part of this parallel run is that you need to have this new batch program written that can read results from both the legacy monolith as well as the new microservice and then compare the results accordingly. Right. So having discussed these two patterns of Strangler Fig and the parallel run, I would like to share an article where we have a real world example of how the Tanzu Labs approached migrating a business critical system from a mainframe infrastructure to a microservice architecture. This case study was about how we successfully modernized a 30-year-old system with over 12,000 programs that is relied on by over 3 million users and runs over a mainframe. The link in the slide deck shows us how incrementally we brought in the Strangler Fig pattern, and we also used a parallel run with the comparative model to ensure that the results from the new microservice and the mainframe were always in accuracy, and slowly we moved away from the mainframe system. For the Strangler to work, we need to be able to clearly map the inbound call to the functionality we are migrating. For example, in the figure shown, we would like to move out the functionality C into a new service. However, the functionality C is triggered as a result of multiple inbound calls to the monolith. Therefore, we cannot clearly redirect calls from the perimeter of the monolith. Instead, we look at a new technique called as branch by abstraction. For this, we need to make changes to the existing system. The first step is to create an abstraction that represents the interaction between the functionality C and the functionality A and B. With the abstraction created, we now need to refactor the A and B functionalities to use the new abstraction point. At this point, there should be no changes in the system functionality behavior. With the abstraction in place, we can now start working on a new implementation of the abstraction layer that will mostly function as a client calling out the actual microservice. It is important to note that although we have two implementation of the abstraction, only one implementation is active in the monolith. At first, we could only use the existing functionality until we have completely tested our new implementation and the service. Once we are happy with the new microservice and its behavior, we can switch our abstraction point to a new microservice and the old functionality is no longer used. Eventually, we would remove the old functionality and the abstraction point to use the new microservice directly within the monolith. So this pattern has some key challenges. First of all, you need to make changes within the exit monolith. And second thing is it brings in a lot of complexity in terms of adding an abstraction layer, making sure that the integrations are in place and the functionality is not impacted. So as we build new functionality into microservices, we do not want these new services to become tightly coupled with the monolith. By giving them deep knowledge of the monolith's internals and integration, the anti-corruption layer is a way of creating API contracts that helps in integrating the legacy monolith with the new microservice without allowing the domain model to corrupt the domain model of the new microservice. So in the book by Eric Evans, Domain-Driven Design, he discusses the implementation of anti-corruption layer in three ways. The first, a facade, which allows us to integrate with the monolith in a much more simplified way. For example, assume that you have to make three different calls to A, B, and C functionality within the monolith. You could have a facade layer which exposes a certain single unique endpoint which the microservice can call. The second is an adapter pattern. This is basically this adapter pattern handles incompatible interfaces between the monolith and the microservice. For example, the monolith receives a soap-based request, and your function, your microservice basically interacts using REST. The translator pattern is basically where we transform the request and response domain model from the monolith to the microservice and the vice versa. And in some cases where you do not have the feasibility of changing the monolith, you would basically go with the facade to monolith, where you would have a facade outside of the monolith and it would interact with the monolith through its standard interfaces. And in some cases, you would have where you can change the monolith code. You would build the facade within the monolith, which simplifies the whole integration and exposes a single endpoint. And if required, you can bring in a combination of another anti-corruption layer, such as an adapter, which helps gluing the code between the monolith and the new microservice. Now with the anti-corruption layer, you have certain challenges. The first being that because there's a new component which sits in between the monolith and the microservice, you could observe a certain amount of latency. And second thing is you have to manage the non-functional aspect as well as the management and the maintenance of the anti-corruption layer itself. And finally, we will want to discuss about the change data capture pattern. This is used along with a Strangler fig pattern and helps us with data synchronization, where we want to maintain a sync between the data between the microservice and the monolith. Now assume that in the monolith you have to migrate the functionality A into a new microservice. The first thing we would do is basically have the reads from for the functionality A redirected to the new microservice using the Strangler fig pattern as described in the previous slides. So the way it would work is the writes will continue to happen in the monolith, right? And the reads will continue to happen in the new microservice. Now for the new microservice to fetch the latest data, we would bring in something called as a change data capture. You have tools such as Debezium, which looks at the database of the monolith and basically captures all the changes to a certain set of tables and then streams those changes through a message broker such as Kafka, which will eventually be propagated to the microservice database. So this way, all the writes happening in the monolith are propagated back to the microservice. That's the first step. Now moving on to the second step is to basically have the read and the write happen at the new microservice level. So you could have your changes made to the proxy, which will redirect all the traffic for the functionality A to the new microservice. But in some cases, you would want to read some certain more data from the monolith, and you would also want to push back changes for functionality A back to the monolith. In such cases as well, you could use a change data capture, which allows you to read the changes from your new microservice database and stream them back to the monolith database. So this pattern is quite popular and used with tools like Debezium and Kafka, and make sure that we have the data synchronization in place. One of the key challenges with this would be the eventual consistency for read in the first step, because you are using an event-driven architecture and propagating, your changes would eventually reach the new microservice and there was certain delay. And because you are bringing a new component such as Kafka and Debezium, you need to eventually have a more complicated setup. So those were the different patterns which we have predominantly used in other engagements, and to help modernize legacy applications and incrementally move them into a microservice-based architecture. Lucas, do you want to pick up next?
Absolutely. We spent the better part of the presentation discussing why enterprises would benefit from a lean approach to app modernization, and more importantly, how Labs accomplishes this feat. But what are the benefits? First, alignment with business outcomes can be achieved through our set lean approach by delivering incremental value. Second, our tight build, measure, learn loops ensure that we can achieve the set outcomes at a high speed. In other words, in a matter of weeks, not months or years. Third, our feedback loop allows us to properly manage risk by validating assumptions in manageable sizes, allowing us to discover whether to pivot or persevere immediately. And finally, our team philosophy of pairing ensures transparency and a proactive approach to learning, ensuring that your enterprise will succeed well after we disengage. That ends our presentation. I hope it was informative, and I'd like to thank everyone here for taking part. Have a great day.